So my name is Yaroslav Halchenko. I'm affiliated with Center for Cognitive Neuroscience and also Center for Open Neuroscience, which I'll talk shortly about. My Twitter handle is Yarikoptik, which is the same also on GitHub and many other social portals, and I will talk about all these projects below there. And the title is Open Science Tools, right? Oh, right, so here we go. If you want slides before we upload them to GitHub, that's the URL. You could point your fancy phone. It might work. Jeremy, did it work? Nope. Okay. Okay, see? Android, I bet, right? Okay, good, good. Linux, right? So take the message. Okay, so the title is about open science tools, but really, it's not the tools which make science open. It's you. You're the tool, right? You could use open tools, right, to make open science. And I had that saying, oh, doing open science with closed tools is oxymoronic, right? Because it's kind of not fully open if you use closed tools. But through the years, I became more senior, right, maybe, and kind of acknowledging the fact that, there is nothing wrong with using MATLAB, but you need to use your tools correctly, right? It might not be as efficient, right? As Luke pointed out, you might need to use some other tools anyway. You will not be able to share the code so others could replicate it. But still, you could do your best effort, right, to make your product open, right? Your code open, data open, and you might still use those closed tools. So it's, again, will not be that efficient, right? And on that note, right, whenever I advise people to do that, like, oh, you could use closed tools, but, then you might still be better off than you were before. And then people say that I'm giving unsolicited advice, but here I'm giving solicited advices, so I'm okay, right? And still, you might be wondering who I am and what is my kind of function in life. Who saw Survive Style 5+ movie? Nobody, huh? Okay, so my function in life, or the goal, which might become your goal as well. Maybe not the main goal of your research, right, because you are interested in networks and dynamics, but this is the achievable goal which everybody could do, to make neuroscience a better science, right? And all these kind of open ideologies, open tools contributing back, that's the steps to make it happen, right? So I hope that that will become your goal as well. Okay. If you want to know more about me, the projects, just go to centerforopenneuroscience.org. We're not yet official center of Dartmouth. If anybody has a few millions to put endowment, talk to me. And that's where we overview the projects and our principles. And our principles are, first of all, of course, for open science, open source is important. And open source here goes beyond just open source software. Your data should be open source. And open source in the sense, not that, oh, I dumped the statistical maps, right? And I don't provide enough details how I've got there, right? Open source means that, like, we wouldn't be able to use those open source systems if we couldn't build them from the source code, right? GPL license even explicitly says that you must be able to build the software from the sources provided, right? So open source goes beyond software. And another aspect or principle is reuse and integration. So instead of inventing something new which might be duplicating what others already did, we're trying to reuse and just integrate pieces to provide maybe better value for existing pieces. Dissemination. So we used to just host a booth at SFN and OHBM just to tell other people in the field what other tools are available which they might not know about. Because there is so much. Luke presented tip of an iceberg, right, in this kind of diagram, what is out there in Python world. And there is beyond Python, there is like all kinds of toolkits, right? And we just don't know what is there. So that's one of our goals also, to let people know what's going on. Quality assurance. So testing, although it was kind of, cool features of Python. No, that was the battery within Python which made it work. So Python came with unit test framework. So unlike in MATLAB, okay, who codes in MATLAB and wrote a single test? One person. Okay, who codes in MATLAB? See, here we go. So MATLAB doesn't come with built-in testing framework. And that also, it does now, right? And there is even better one maybe developed by Nick Osterhoff, who was postdoc here, which is called MOX Unit, I believe. So it works in MATLAB and Octave. It's kind of nice, and took ideas from Python. We tried to pull him into Python world, but he resisted and went back to MATLAB and implemented, kind of having learned Python, implemented those ideas in MATLAB. Anyway, quality assurance testing is a great thing. If you are to learn something here, it might be the best thing you would learn. Okay, anyway, convenience. This is kind of never will become a buzzword like reproducibility, right? Dissemination, right? Convenience is really important. If things are not convenient, it's not convenient to install things, you're just wasting time, right? And then nobody would be able to replicate because it's not convenient, it's not easy. So convenience is important. In all our projects, we are just trying to make things more convenient. And community, of course, is maybe the largest of it, right? There is no point to make anything open if there is nobody to take advantage of it or work with you together. Anyway, okay, so who are we? Majority of the projects I'm working on are work together with Michael Hanke from now Jülich Research Labs. He used to be at University of Magdeburg. So see, I didn't even just on the web. So he moved to Jülich, and Joey Hess, who is the author of Gitanics, which I'll talk about. And there is other goer, Kyle works with me, and then Benjamin works with Michael, Alex, Michael sysadmin, and we had and still have students and interns working with us, although some of them parted and some of them stopped talking about it, so they've got smaller icons. Anyway, okay. And there are common suspects, affiliated faculty with the center. You will probably hear about their tools. Luke already mentioned quite a few. But that's just tip of an iceberg in our kind of day-to-day interactions. We pester many of those projects, right? And many people pester us. And work is supported by various grants. And I'll mention a new grant which we've got to work with Matt. Okay. And if you want to know kind of more about principles, one of the papers mentioned here is 4 aspects to make science open by design. And this principle, open by design, is what I want to talk about next. So open by design 101, kind of. And first item is to prepare share, even if you might not be sharing later on. So what does it mean? So first of all, use instead of disregard legal aspects or mechanisms which you could deploy. Assign a license to your code and make it official. And that will help you back later on. If you move on to another institute, and apparently your previous institute wants to just grab possession of your data and code, you say, but I did it already released under open license. Maybe copyright will be of that institute, but you'll be able to use it. So it's kind of tricking the system with its own mechanisms, and it's really important. Another one, it's again kind of start from the beginning, and you'll see that many tools which I'll mention will kind of introduce that notion as well. Invest time to do things right from the beginning. Might be with your study design, you don't want to fix it later on. Might be with how you arrange data collection, so you don't need to spend lots of time converting data later on. So just invest maybe a little bit ahead of time to make your work later on more efficient. And even, okay, who uses shell? Everybody here. Right? Be brave, be bold. So everybody uses shell. And if I ask you, are you kind of convenient and efficient? Many of you will say, yeah, sure. And then when I will sit behind and look how you work in the shell, I'll see that it's like go left, go right, go up, go down. And just learn. There is tricks how to make your work in shell more efficient and even more reproducible. You don't want to re-enter the same command when you need to change one character. To bring it from the history. Your history might span years. You don't know, but read there and how to make it happen. And that was really useful for me sometimes. I was like, how did I do that analysis in this directory on this file 3 years ago? Who would be able to answer that question? Nobody, right? I looked up my bash history. I found that specific command. Oh, that was this flirt and whatever, right? So it was possible to discover it from the history, and those tools are available in every laptop, even on Windows boxes. It's amazing, right? So just learn a little bit more, and you'll become more efficient down the road. Automate and script it whenever possible. Question?
Question. So, I mean, I also thought about this, and then, like you said, there are so many cool tools, or even just like code snippets, or like nice, like how you do a certain command and so on. And I was just curious to hear kind of your suggestion how to keep track of this, because you mentioned keep good record of the actions. Of course, if you implement them in a project, and then they are somewhat documented, but then you also come across all these other cool like tricks, programming tricks, and I'm still looking for an option how to like nicely document these for myself to kind of.
That's a great question. So how pretty much we put those into practice, right? It's infeasible just to go read the book and immediately apply all the techniques you've read about. So in my case, I advise skim through something new you found to kind of deposit it back into your memory. Then later on, if you're doing something which you feel like, oh, this is inefficient, somebody should have done it already. I would Google it, or maybe remember, oh, I've read about this there. Then I go and extract that specific knowledge which I could apply now, right? And through repetition, that's how you remember it, right? The same with this kind of simple shell thing. It's like, oh, you discovered there is Control-R. Just look up the history, find the command. You use it once, twice, 3 times, then it becomes in your fingers and you forget that you had to learn about it. So it's kind of, learning should be incremental and small steps. Sometimes it's kind of useful to get a glimpse. Like you say, oh, there is all those toolkits, you've heard about Seaborn. Later on, I want some fancy plot. Oh, I've heard about Seaborn, let me read how I do this, right? Kind of this iterative with some glimpse over bigger ecosystem from time to time. I would say that. Okay, so automation. It's perfect, do it whenever it's possible. But then, remember the theory kind of diverges from reality in times, right? This is XKCD comic, and typically we think that, okay, if I was working on the original task, I'll spend this much time. Over time, my load will decrease because I'm done. If I write the code, my load will be kind of high, but then automation takes over and I have more free time. Okay? But in reality, just you write the code and you debug it, and then it's just ongoing development, and you are kind of deep entrenched in this, right? So, do you remember my slogan that don't reinvent the wheel? Once again, if you feel that something should have been automated, most likely it was by somebody else, so you need to do a little bit of research how people did it, right? If you find something which fits your needs, 90%, but not 10% you need to kind of tune, that's the optimal opportunity to contribute to that project. Instead of redoing the whole 100, right, and getting entrenched into this debugging and whatnot, you go to existing project, you will learn so much more and so much faster. And then, also you will offload user support, right? Because there is a project, they have user support, so you kind of interact with the project for a while, then you move on, and if they adopted your contribution to their code base, they're It's kind of shameful to say that, but that's what happens, right? People move on, right? And if you have your own project, then you're the one to provide the support for eternity, or just say, oh, it's dead, right? Okay, and get creative faster. Now they put, like many projects, reference is done through Zenodo. If you're a contributor, Zenodo automatically puts you among co-authors, right? Wonderful, right? You contributed, you became co-author, you get cited, and I'll talk about due credit later on.
How well in practice is this stuff working with the fact that as things change, of course, they're no longer backward compatible? I mean, this is true of both closed and open code, and in practice, just becomes an issue of how much. If you end up writing it all yourself, you end up with complete control, and you know that it doesn't
you end up without control. You need to implement all control for backward.
But in practice, anytime these kind of things shift over time, right? This is we were talking about Python 2 versus Python 3, right?
So, contributing to existing project will contribute to longevity of your effort and backward compatibility as well. Because there will be others who will be either doing mass migration. That's what happens also in Debian. Sometimes we just mass migrate packages and contribute back to upstream. Because it's, if you get into this mood, oh, we are going from Python 2 to Python 3, we've learned how, and then we apply that knowledge through the wide spectrum of packages instead of just me alone, I have a package and now I need to do migration, right? You could kind of nail yourself down in the environment where it works on Friday, and you do it only on Friday in that environment, right? But that also doesn't scale. You all hear about containers. Containers, another kind of really nice way to freeze yourself in that environment which works, and don't worry about backward compatibility. But this is not a solution, it's just an escape. We'll talk about that. Testing is important. That's what's important for testing your backward compatibility, that your changes don't break anything. So if you learn something, you learn testing. Okay, and third advice for open by design. Community. See something, say something. Don't be silent. If you try the tool, it doesn't work, report back. Research first if somebody reported already, right? But don't just ignore it. Oh, I couldn't figure it out. Give me an error. Right? An error maybe was meaningful. By the way, I didn't put it here. Read the error messages. Sometimes even read warning messages. They sometimes, or most often actually, provide you information why things didn't work. And then report back. Don't be silent. I believe even Yaroslav made his hackathon project once to be Yaroslav for a day. To just complain here and there. Because it's hard to complain, right? Especially to complain constructively and informatively. So this is some recommendations there. People create their, maybe there are better ones. But the best bug report is reproducible bug report. If you ran into a bug, try to reproduce it and provide sufficient amount of detail so others could reproduce it too. Okay. Talking about reproducibility. Within our repronim project, if you go 5steps.repronim.org, here we go, actually, it redirects here as well. For any study, in our case, there is many people who do MRI here, many do electrophysiology, but kind of general workflow applies. Study design, data collection, data processing, statistical analysis, publication. If you go through these steps, which mention the tools, which we'll talk about, they will help you to become not only more reproducible, but more efficient. And again, think ahead of time. That's why the pre-registration here, which I will not talk much about, but third item here, pre-register your study. In our case with one of the interns, Oli, we decided, oh, let's do pre-registration. It should be easy and quick thing, right? We just say what we'll do. No, it took us thinking, what we actually will do, right? So it will not be just wild walk in the forest, we do this and then try that, and until we get some significance, right? We had to think through what we'll do, and then the last item was the best. Have you simulated your results or analysis, right? No, we didn't. Well, let's do that. And we simulated data, we ran our pipeline, discovered the bugs, fixed the pipeline, simulated, again, noise, and then we simulated real data. Our results confirmed, our pipeline produced what we expected, and then we switched to real data. That was super useful, right? So we didn't have to just get the blobs and then describe it, right? We actually had confirmation that our pipeline works correctly. So registration is quite cool. But also, so first item here, and I'll just switch to this. So problem for open data sharing awaits from the beginning that your image and data, to be called open, right, should be shared. And if we don't incorporate sharing inside consent forms, right, for animal research probably you don't ask them much. For humans, right, we need to get explicit confirmation ideally from the participant that data will be shared after sufficient anonymization. And even that is not trivial, because in known data sets, such things happen. Data set is published, then university discovers that, oh, okay, apparently we didn't ask the participants, and they retract the data set. So your open things could become not available, right? So think ahead of time. And there is such a project, Open Brain Consent Form, which kind of stems from the interesting effect that we have centralized law for all the subject protection, we have centralized committee, right? But it's all interspersed through per institution, what is it, IRB boards, right? And every IRB board has its own mind, right? And they demand, oh, if you phrase it this way or that way. So in this project, we collected sample consent forms, so you could take some others, sample consent forms where there is some provision for data sharing. And Chris Gorgolevsky also provided consent form, which we called ultimate consent form, which they use for some studies at Stanford within OpenFMRI kind of framework. So there is English, I believe there is German version, there is, I believe, even Spanish and Chinese, maybe 2 versions of Chinese. So you could take that language, put it in your consent forms, approve it, have it approved by IRB committee. There are precedents from other institutes where they used it successfully, so they couldn't just say, oh, this is blah, blah, blah. If there is some problem with the wording there, file an issue there and we'll see it resolved. Okay, and then we also provide some pointers to anonymization tools. Again, think ahead of time. Sometimes people, let's say OpenFMRI, Open Neuro platform, they deface all anatomicals before even putting them into pipeline. So they are assuring that whatever result they get, they could be reproduced on the data they will share later on, right? If you run your analysis on non-defaced anatomicals, right, and then you share only defaced anatomicals, results might vary, right? So again, just thinking ahead of time, and this is the tools you could use. So get involved, as you mentioned, there is no logo. If you have any artistic kind of predisposition, please contribute. Everything is on GitHub, submit fixes, spread the word. Okay, no questions about that. So next problem, and it's again about data. And here we have a good mix of electrophysiology, and I'll mention something about that later on, and neuroimaging. So, who is doing neuroimaging here? Good part, right? Who is collecting or organizing your data in bits data sets? Good part now. See, there is progress through the history of humanity. People converge in bits, right? That's good. And what is bits? Is brain imaging data structure, and sounds fancy, but what it is really, and I'll introduce this referencing project, but what this BITS project is about is really exciting topic of how you name your files. So, we take files on the left, which are DICOMs, and we convert them into hierarchy, which represents this data, right? And that's kind of important. But the beauty of it is that if you have seen one bits data set, if you got familiar with it, you've seen them all. You could go to any bits data set and immediately you recognize what's going on there, right? In electrophysiology, there is a problem. There is no even common format for data, right, files, not to say how to name them, right? So hopefully we'll get there because bits already supports not only MRI data, but EEG, MEG data, intracranial EEG, so we're just converging at least how we name our files, right, and the data formats. And how is it important? Because with this convergence, we could, first of all, pretty much talk the same language, computers and us, right? We could look at the data set, understand what's going on in computers. Programs could read those data sets and process them efficiently. Then compliance could be checked. Bits validator, it's like unit tests, it's a boring thing, right? And just to validate that everything is kosher. It's huge. Question?
The biggest issue for both the MRI and the EFIS data has been the behavioral metadata.
Mm-hmm.
Do you have that?
Oh, metadata is a separate topic.
No, it's not. No. Metadata
Hold on. It's not a separate topic. It's yet another bigger thing, right? So, first of all, the main principle of bits is that we fulfill 90% of the use cases. Okay? So, metadata is super important and we'll get there, but you need to start somewhere. First, you agree how to name your files, right? Then you agree on some metadata fields which are associated with those files, right? So, not behavioral, but maybe technical ones which you could extract. Behavioral data, there is also already ways how you describe it. Let's say response files or events files in bits. They're super simple. Onset, duration, I believe, and what kind of event. But then there was contribution. Oh, in EEG we have this complex within the trial something happens, right? So there is hierarchical description now, which is described in bit format. So you could go read about that and put your data in that format. And then bit validator will validate that nothing is wrong with it. Using bit validator on early collected studies, we already found, oh, why there is like discrepancy, why these subjects lack this file, why resolution starts to change, and fix it again early instead of after you collected all the 100 subjects, you realize that, oh, there was some fluctuation in the force, right? And you don't know how to address it. Okay. And then there is many tools to help you work with those data sets, like PyBits for Python, there is Matplotlib built, and then there is bits apps. Bits apps are cool, right? You just give it a data set, right, which is in bits, and tell it pre-process it, right? And it just pre-processes it, right? You just give it few options, and regardless of what study is, it provides this kind of really unified way to process things. There is a bunch of URLs, and okay, so bits. The problem is that how do we get to the bits data sets, right? So if you're collecting the study, it's all those bunch of diagrams, will you rename them manually? What we decided to do, we came up with a convention, how we name our sequences and organize our studies at the console. So now, people invest 10 extra minutes to name their sequences consistently across their studies. 10 minutes, maybe 15. Sometimes maybe none because they just copy-paste, right? And that's it. Later on, we collect these sequences and we use QDConf with data that I'll mention later, which automatically lays it out as bits data. So with investment ahead of time on a green, how you name your sequences in the scanner, we gained now convenient, uniform way how to convert all the data sets which we acquired here at DBIC into bits data sets. Sounds cool, right? Okay. And the whole acquisition works like this. We have DCM4G text server, which receives the data, puts it into files, then run QDConf with recurring heuristic on them. It also optionally puts it under data lab control. All of this environment is served in a Singularity environment. If you haven't heard about Singularity, you might hear about it later on. It's like Docker, but geared more towards scientific computation. And then those data sets are already in data lab, so we could use it as a Git to distribute our computation without losing control over which version is where of the data, and get incremental updates on those data sets as well. So Reprim provides, again, minimal time investment ahead of time, and then you get many benefits after from there. And all data sets in the center are now organized consistently within the hierarchy on the server, so we don't need to look around where is bits converted data set for that PI. So it becomes really easy for a center to just manage the data sets. And also sidecar JSON files provide already not only extracted metadata, but fields which need to be filled because we don't know what is going on. Let's say, which task ID was it, or which response behavioral data put it in, right? And DICOM files are still there under source data, so you could reconvert later on. And all data is under data lab, which I'll mention later. So, get involved. First of all, first advice for everybody doing neuroimaging, collect DICOMs, not some nifties or parregs on anything else, which scanner might spit you out. At least DICOMs should have most of the information and metadata which you might need later on to discover facts about what actually was done and how it was collected. So use QDConf. Reprim is just a heuristic within QDConf. Spread the word. Questions? No questions. Okay, next problem. We've got a problem, and that was back in 2007, right? So we've got a bunch of data, and then, back then, there were no standard software for doing machine learning data-driven analysis of neuroimaging data. So, and now we'll talk about, and of course, secret. Now its kind of situation is different, right? So we have NiLearn, we have many toolkits for machine learning analysis of neuroimaging data. Back then there was nothing. There was a secret Matlab script for doing searchlights, right? Which was circulated behind the curtain. Otherwise, there were no search-like possibility without coding yourself. And you could, do things wrong many, many ways, right? So we decided that instead of just doing something and keep it for ourselves, we'll start project PyMVPA, which is Python multivariate pattern analysis. And indeed, it was initiated in Princeton. But then Jim moved to Dartmouth in 2008, and me and Michael, there's the Michael, that's that German, which looked much older earlier, and Per Soderberg was also in the crew. So we started PyMVPA, and our main goal, and that was 2007, Python was 2.2 maybe, something like that. So it was a while back. But even then, Python was cool, so we could have scripting interface in Python and also wanted some in command line. We wanted documentation. That was before Sphinx was born, but then it was born, so we jumped on the wagon right away. Extensible. So actually what another beneficial part of Python was that you could link to those C libraries. It wasn't like in, I don't know even how you do it in Matlab either. It's easy to link to arbitrary dynamic library. In Python it was possible. It's like you need to mess with all the data types, but it was possible. That's how we decided, okay, we will not reinvent the wheel. If there is a library which does already something in C, or coded in C, we'll just interface to it. That's how Per contributed SMLR algorithm implementation. It was in C. We just interfaced it from Python. And portable, so it should have ran everywhere. And here's the proof. Actually, in 2009, we discovered that it was used for some unknown reason. It wasn't for neuroimaging, right? To drive some robot, actually done here at Dartmouth before we even came. It was amazing. Anyway, so it was quite portable and reliable, right? So from day one, we started with writing tags. I don't know where we would have ended up being if we didn't have tags. It's just impossible to develop anything if you don't have any assurance that things don't break, not even through your work, but through changes in external libraries, through changes in versions of Metadata. Okay, and free and open source. So we are MIT licensed, and here is a quick introduction for you, again, into Python, right? So you're flying, and the main command in Python is, of course, is import, right? So if you import anti-gravity, you get the superpowers, and in our case, we import, in this case, everything from MVPA to Suite. So it'll pollute your environment with everything, Matlab style, right? So just everything is available, right? And it makes it kind of easy to code because everything is available, but it's really bad practice. Ideally, you just do import MVPA.suite as something like MV, and then MV dot would reference all those objects. But here we go. So Matlab style. How difficult is to read a data set in PyMVPA? If you have multiple runs, you just specify here a list of multiple runs, and then you specify also what were the targets for any given condition, and chunks is pretty much your runs, independent acquisitions, and you provide a mask, because typically we don't analyze the entire volume, but concentrate on either brain mask or specific ROI, and then we could add additional attributes. So this data set which you're getting from PyMVPA, it's not just NumPy array. It has all those additional attributes assigned either to feature attributes, which would be like voxel coordinates, right, voxel indices, and temporal attributes, or sample attributes we call them, which could be time indices for your volumes, it could be your conditions, or it could be runs, right? So similar to some degree data frame in pandas, where you can have complicated index, right, which would say that this row has these attributes. We have this data set which you can easily manipulate, select specific feature while retaining all the attributes, all for time. And but for machine learning algorithms, it looks really benign. It's just a matrix, right? It's just an array. So that was the idea. We take complex data and present it in convenient form for machine learning algorithms. So how difficult? Oh, here we go. Let's say to select only ventral temporal. We just do this, right? Which looks like NumPy array operation. We select all samples and only select those features which come from BT. And you get out here another data set which still retains all the information about not only attributes but also how to get back into original 3D space if you later on want to visualize something from there.
So you could get the summary, which will tell you how many runs, how many labels of each run, so you could investigate your data set about its properties. And then how difficult it is to do cross-validation analysis. Let's say with a classifier, it's quite trivial, right? You just choose the classifier, you stick it into cross-validation, you specify how you cross-validate, and you enable, potentially if you're interested in more fancy operations, like here we enable statistics, so they're available from conditional attributes, and we could ask for pretty confusion metrics, right? With all kinds of additional characteristics extracted from it. And you could even plot it. This is as it looks plotted by PyVK, so there is no Photoshop enough. So the idea was to create publication-ready visualizations for machine learning tasks and mirror imaging. And then, if you have heard about searchlights, who knows about searchlights? There we go. Good. And here's an introduction, nevertheless. So what is Searchlight? We have a data set which is full volume, full brain volume. And then Searchlight is just an idea that you take some local neighborhood, right? You take only that portion of a data set. That's where you see probably the previous feature of just dealing with this data set which retains all the attributes together, right? And then just analyze it, and that there is a brain in there, but for some reason it doesn't show. So, and you move this searchlight through the brain and put the results into corresponding center voxel location, right? So that was how it was introduced by Krieger in 2006, right? So we decided to implement it. How difficult is to modify this code if I want to do this classification in Searchlight? And it's just one line. You say, oh, take this, right, and do spherical Searchlight using this function as to do in each block, right, and use this radius. And that's it. You get your map, and you could map it back into a Nifty file and plot it with whatever fancy software you use for your visualizations. So that was the idea, that concise scripting language to do maybe complicated things. Now, that searchlight, it doesn't have to be in the volume, it could be on the surface. It could be surface-guided volumetric searchlight. And you'll probably hear from James Haxby about hyperalignment. We have all those flavors of hyperalignments in there, including the searchlight and connectivity-based. It's everything in PyVK. And you could save it into files, and with this tool and pretty much that code, we could have done we could do different analysis. We could apply it to EEG, which has also some spatial kind of continuity between the electrodes. We did it to MEG, we did it to spikes recording to show that beyond statistics of independent, spiking rate at specific time and specific electrode, multivariate combinations might be also useful to decode specific construct. I don't remember even what conditions were. And of course to fMRI. What we could do also, transfusion, how we called it, is to predict fMRI response from EEG data. It was kind of cool and part of my dissertation a while back. And what we could have done, maybe actually analysis what we did with Ross Poldrack and Steve Hansen before we started to work on PyVK together, decoding mental states across different studies, right? And looking at the sensitivity of the classifier, which is pretty much what it was. In that case, it was just artificial neural network, and provide loading of different terms for different maps which we extracted from these sensitivities. And although we didn't update that page, and it's a boring task, go look and put people there, who use PyVK, but it's used quite extensively. And you could do that too. You could go through the tutorial, and by the end of this month, I promise it will be migrated to Python 3, so it will be modern as the rest of the world. Okay, and the problem with migration is actually tests. They actually find what is broken. That's boring, right? If we didn't have tests, I would just 5, 2, 3, done it, it seems to work, you release it, and everybody's happy, right? Tests, they give you that pain, right? Because you convert and it's like, oh, it's broken now. What's going on, right? Okay, anyway, so I showed that it was portable, but it was even enough portable that it ran on my smartphone in 2009, right? And that's what motivated some people to install it. Like, hey, if there is a dude, right, with a freaking phone and he runs it, I could install it as well, right? But, oh boy, there is mismatch between the order of the slides. Here we go, motivation. So, but the problem was that 12.5 hours later, and that was a while back, right? He still failed to install it on Mac OS, right? So whenever Luke mentioned that sometimes it's difficult just to install the software, although today I hope it will be less pathetic that whole day we will be installing things, right? Because that's not the problem of research interest, right? So that was the problem we were trying to solve next. We used dozens of scientific software projects, right? But deployment and maintenance of them is sometimes quite non-trivial. So that's how we came up with NeuroDebian. Because in our case, we already used Debian system, and we decided, oh, that's how I got to know Michael. We were bashing about FSL on some Debian mailing list. It's like, oh, he looks like me, or sounds like me, right? So let's just work together on that. And only later on we recognized that, oh, we are also interested in machine learning. And then later on we recognized that our advisors are actually friends. But that's okay, long story. So, again, software, difficult to install, and the problem is also that no software is written by God. Actually, nothing is done by God. Oops, sorry. Okay. It never said that within 7 days, God created MRI machine. Right? So whatever we are using is not created by God. Again, kind of sounds wrong, but whatever. So everything what we are using is created by humans, and humans make mistakes intentionally and non-intentionally. So everything has bugs, right? Software has bugs, scanners have bugs, everything has bugs. So even data can have bugs. And what is bugs in the data? Typically, it's a result of buggy software or incorrect kind of assumptions applied to the software, to the data. Okay, so, and that makes our research software particularly not rock solid, right? Because it's too few users, unlike, let's say, Microsoft Windows. They don't need tests. They have millions of people, right? You just dump it upon people, they report the bugs, and you're kind of figuring out how to fix it, right? In our case, we have only few users, right? But sometimes, you know, software bugs are critical importance because they are producing our papers. And we don't want swarms of papers being retracted because we've forgotten to transpose the metrics. And that's not a tale, that happened. High-level profile journals retracted a bunch of papers because apparently transposition wasn't done, and the results seem to be okay, right? Apparently they were not. So testing is important, but bug reporting is also kind of difficult. We don't know if we use some software, where do I complain, right? So insufficient also inappropriate testing, quality assurance, and of course death by PhD phenomenon, right? So if you start your own project, you move on, project is dead, right? So it's difficult. And that was again 2007, 2009. So situation was broken by design, right? So there were no funding available to create this research ecosystem of software. And development of scientific software, especially then, wasn't considered anyhow related to scientific progress. Now you could see initiatives where, you know, there is investment is actually making them happen. So what we decided that we develop a platform which will be used by anyone, right, available to everyone, and will guarantee availability of things, like that software will still be available, possibly in that same version for eternity, right? And that all the software is available in a single environment. Unlike, let's say, even if you're using FSL, in our case it was PyPL, we want one way to install everything we need for our research, right? So it was somewhat utopian idea. Okay, so we decided to join the Debian project, which already provides over thousands packages for all kinds of things. It's not only for servers, there are people from different scientific fields providing software there, and it's origin of many distributions. You've heard about Ubuntu. So if you're using Ubuntu, you're running Debian pretty much. And if you're running Debian, you're using NeuroDebian, which was our project, where we could just adopt those technologies for Debian, merge or integrate our software of our interest inside the Debian, so others could help us also maintain it, right? Because there is thousands of other maintainers in Debian which provide us fixes. And of course, we come up with a fancy logo, so Michael was in Maine. You could do your alignment algorithm. Okay, anyway, so if you want more detail why and what for, there is a paper, open is not enough. And how easy it is to install things in Neurodebian, at least if you don't care for bleeding edge FSL 6.0, installing FSL is as easy as installing Edit, right? You just say install it. It's your pretty much app store for scientific applications as well. These days with Conda and other distributions, there is other ecosystems now as well which make it easy, but typically they're language oriented, right? With Conda you have some non-Python projects in there, but typically it's just Python. So you would end up using Conda to install one thing, then FSL to install another things. In Debian the idea is that we are agnostic to the language. Whatever you need could be packaged and provided through the same unified interface, or you could install collections of packages with the same easy command, and then you could keep your system up to date. My laptop probably went through migrations already through upgrades for the last decade. I just go and, oh, there is new release, okay, let's upgrade. And I just keep upgrading, and it still works. Okay, anyway. Another interesting point is that because there are archives of Debian, we just piggyback on them to kind of establish this reproducibility aspect. If you found now some paper which used Python 1 point whatever, 5.2 in 2002, and you want to rerun that analysis, you can do that. You could create that environment from archives of Debian and just enter there and run it. And who knows how to create Docker images? Okay, some people. So those who know also know that if you do it today and tomorrow, you might get different images, right? Because underlying, let's say, apt repositories might change. So to facilitate that, we came up with the tool ndfreeze. So you just say to which date to freeze apt repositories of Debian and Neurodebian, and then you have some guarantee that you will be reproducing the same environment if you happen to need to rebuild it to add another tool. If you rebuild it without freezing, add another tool, other tools might get newer version as well, so now your two images will be different. So that might be handy. And you've mentioned maybe that there is this generated by Neurodocker version, blah, 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 blah. So, and this is Singularity file, not Docker file. There is a tool which is developed by Jakub at MIT, which is called Neurodocker. Although it says Neurodocker, it is not that much Neuro besides custom support for installation of additional tools not outside of, let's say, Neurodebian. So it will build them or download tarballs from upstream directly. But otherwise it also supports Neurodebian, so you could just, in command line, say, oh, give me a Singularity image recipe which will install this and this and that. So it's an easier way to generate those Docker and Singularity recipes. And if you want to know more, go to our poster from HBM this year about fantastic containers and how to tame them. And maybe you'll learn about Yoda principles as well. It's a nice guy. And there is also a nice kind of flow of things with how we advocate to use containers. Where Neurodebian is available? 5 minutes? Okay, we'll get to DataLab really quickly. So it's available by installing it, or you could use Docker and Singularity images, which we provide. Okay. Here we go. Yet another problem. So we have data in nice format. We have software distributions. We have containers, so we could package everything together. But then data always felt awkward to us, right? So we maintain our code under version control system. We have Neurodebian with software packages, but we cannot stick data in there because it's too big. Although we did, but it didn't work as nicely. So data was really second-class citizen in all this ecosystem. So that's how the DataLab project was born. And it was funded by NSF for 3 years, and we are waiting for the results on next stage of its development with better metadata support. Okay, so why DataLab? Because tarballs, how we typically deal with data, are inefficient. One file changes, you need to re-download 1 terabyte tarball, right? It doesn't work. And there is absent version of data. Who versions your data? Everybody, come on, everybody versions your data, right? Everybody, we version them, right? We copy them, which is inefficient, right? And then we add some kind of description, right? It's not good. Anyway, and there is no data distributions, or at least there were no until we came about. And there is different ways how you download from different data portals. and it's difficult to share. So, but the idea was to managing data should be as easy as managing code in software. So we came up with Data Lab, which you could learn about more on datalab.org, and that's, first of all, Data Lab is pretty much a shim or wrapper around Git. So who knows Git? Okay, who likes Git? See, everybody likes Git, so you should love data. Okay, so Git is great, right? It's a version control system developed for code, right? But the problem with it that it's inefficient for storing data. You don't want to commit your gigabyte files into Git because that's it. That's the end of the day, right? You'll just wait for it to keep crunching. There was a smart guy, or there is a smart guy from Tennessee, Joey Hess, which I mentioned before. So he developed Git Annex, which allows you to manage data files within Git, like information about where is this file available, without committing it to Git. And that's our second building block for Data Lab. So both Git and Git Annex largely work on a single repository level. Terabytes of data is already out there. So that's what we wanted to do, provide data distribution which would be based on Git and Git Annex. So this one figure pretty much outlines main commands of Data Lab that you could install any data set which is available out there, which might be some Git repository on GitHub. All open your data sets are Data Lab data sets. You could just Data Lab install this thing. And then you could optionally select which files you need for your analysis. You could create new data sets. You could crawl existing websites and put them into Data Lab data sets. You could nest one data set inside of another data set, so you have the full provenance of, oh, I've got these results using that data set, using those scripts, using this environment, inside your Git repository, recorded in your Git history. And then you could publish them. You could publish data to one portal while pushing Git repository to GitHub. Then you could export it. Let's say you could publish that data set to Figshare. And that data set itself will know that, oh, this data now could be fetched from Figshare. And then there is metadata. So let's talk about metadata. We've collected already indexed over 60 terabytes of neuroimaging data available through data. And metadata. Metadata is crucial to find things. So it's data about data. Data about data. So this data lab command gives you pointers to all files which we know about with T1 anatomicals for females of age 24. And similarly, you could look for any other field coming from DICOM, NIFTY, BITS format. Let's say in BITS we have two interesting ones which might be of interest for you. Is Cognitive Atlas ID, which comes from Cognitive Atlas. Many studies annotated that this task is that Atlas ID. Or there is Cognitive, I forgot, an Ontology ID as well, which not that many data sets annotated. And the point is that you could create this hierarchy of data sets, which you install only the ones which you need, but they know about each other, they know where they are. You could publish some data publicly, some data privately, so you have full control over what you can do with your, not only code, but also entire environments and data. And if you want to know more, okay, hold on. There is Dandy project. We just got awarded an Edge grant to work also with that to provide somewhat similar and somewhat data lab based and somewhat BITS inspired, but neural data without borders standard for electrophysiology. Who knows about NWB format? Oh, see? Do you use it already?
Yeah, we try.
Cool. So that's my goal as well. Try it and make it more useful as well. So now I'll skip just a few slides back to give you the summary. Hold on, where's the summary? I will skip Duke Ready project, but you can discover about it later. So my point is that we are in the state now, unlike 10 years ago, that open science is possible, and those tools would help you to become open scientists. And although it sounds utopian, I already mentioned so many tools which provide you assistance, right? So you could do everything. You could start from the beginning and code consent from participants into your consent forms. You could manage your data really cohesively and openly, so interoperability between humans is improved, right? And you could automate many analysis and testing. So pretty much, it's in reach and it's now. Thank you.